Good evening to everyone. My name is Arturo Bacco. I am a PhD student from University of Salerno, and my research is about the effect of welding process on static and fatigue behavior of high-strength steel welded joints. The high-strength steel are different from common steel because they have an higher tensile strength. This feature is given by the way this kind of material are produced. These materials are usually first hot rolled and after heat treated by quenching and tempering. This process gives at this material an higher tensile strength, but also make this material highly sensitive to thermal gradients. For example, during welding, that nowadays is the most widely used process to join two components made of HSS. The market for this kind of material is rapidly growing during last year, also because the field of use for these are various. In industrial engineering for hoist equipment, earth-moving equipment, material transport equipment and storage, but also in civil engineering for viability and building. This because this material, having a higher resistance, allow to design and create leaner and lighter components. How we can see from the literature, the welding can reduce the fatigue life of this material, making it comparable to the fatigue life of common strength steel. But different welding process can affect in different way the fatigue life because different welding process can generate different microstructure inside joint, different sides of zone into the joint, and also different welding bed. Another important aspect is that different welding process can generate different defects inside the joint. For example, porosity, lack of effusion, slag inclusion, incomplete penetration, and also the cracks. Another important parameter for the fatigue life is the bed geometry, because different welding processes can generate different bed geometry that can generate a fatigue critical notch, and this can promote the crack initiation and propagation, reducing the fatigue life. For this application, we use this material, the strength 700 from Sub, with the mechanical characteristics and the chemical composition that I summarized in this slide. We chose this type of material for his carbon equivalent value of 0.49. That means that this material has a good weldability with a lot of welding processes. The welding processes that we used are two, gas metal arc welding and laser beam welding. We chose these two processes because they are very different from each other. Gas metal arc welding is a semi-automatic process done by an operator, needs a groove, it's an heterogeneous process because need a filler material, and generate low energy densities, while laser beam welding is an automatic process, robotized, no needs groove, it's an autogen process and generate high energy densities. For gas metal arc welding, first of all, we machined an X groove on the plates to have the same shape of joint than the laser beam welding. And we designed and creating a clamping mask to reduce the angular misalignment during welding. To protect butt during welding, we used a mixture of 15% of CO2 and 85% of argon. And as a filler material, we used a wire from Lincoln Electric with the chemical composition and mechanical characteristics comparable to base material. In this slide, I summarized the parameter used for gas metal arc welding. All the process was completed in two passes, with a time between passes equal to 4.3 minutes. For laser beam welding, also this process was completed in two passes with a laser power equal to 4 kilowatt, a focus position equal to -3 millimeter, and a time between passes equal to the previous case. To evaluate the quality of the welded joint, first of all, we decided to perform some tensile tests. To do this, we extracted some specimens perpendicular to the welding direction, and we tested it. How we can see from the table, I summarized the main results from tensile tests. And for young modulus and maximum stress, we can see that we have had more or less the results comparable from the laser beam welding, gas metal arc welding, and the values gives for base material. But we have had a reduction of the maximum elongation at break from the base material to laser beam welding, but also from laser beam welding to gas metal arc welding. After tensile tests, we extracted the samples for micrographic analysis and hardness test. We incorporated, polished, and chemical attached it. We performed the macrographic analysis to evaluate the presence of defects inside the joint. We can see from these two macrography, one for gas metal arc welding and another for laser beam welding. No particular defects are present, but we can appreciate the very different sides of a zone into the joint, and also we can appreciate the different sides of the welding bit. On the same sample of macrographic analysis, we performed the hardness test. And from the graphic, we can see that the maximum value of hardness were founded for the heat thermally affected zone 1 for laser beam welded joint, while the minimum were founded for heat thermally affected zone 2 for gas metal arc welded joint. The dog bone spacement were extracted perpendicular to the welding direction, like for tensile test. And the spacement were tested with an axial load and a stress ratio equal to -1. With the data from fatigue tests, we created one Wöhler curves for each welding process. From a comparison of the two Wöhler curves, we can see that the two curves show a near to 2 million of cycle, but for laser beam welding in the finite life zone, we have a slope of 5, while for gas metal arc welding, we have had a slope of 9. In conclusion, we can say that the gas metal arc welding was more invasive because it thermally affected larger areas, while laser beam welding generated high energy concentration in very small areas. These allow a rapid cooling, and we can in this way we obtained more or less value comparable to base material. The values obtained during the tensile test are comparable to the values of the base material, as accepted for the maximum elongation at break, how we have seen. And all the Wöhler's curves show a near to 2 million of cycles, but in finite life zone at the same stress, the LBV specimens show a greater durability than gas metal arc welding specimen. Thanks for your attention.